Alrighty guys, let's have a chat about plate tectonics. So I wanted to get this video up as soon as possible, as you can see, still in the classroom, so that you have it available so that you watch it before the prac on Thursday, because it is directly related to the prac, and it will make the prac make much more sense if you've watched this. So I'll make sure that I put an announcement out once I upload this video. This one might be a bit longer than the previous one because there's a lot of material that I want to cover and make sure that you get an understanding of. So please, if there's anything that you don't understand from this lecture, send me an email or bring the question to class and I'll make sure that we go through it together so that you can grasp the concepts. So what we're looking at today is essentially what plate tectonics are, how the theory of plate tectonics developed, and also what it has to do with how the Earth is structured. So I'm going to go through the slides with you, so I'll refer to each slide whenever they're relevant. Otherwise, it'll just be me gas-bagging at you for a bit. So I'm on slide 2, just looking at the Earth structure. So we know that the Earth is a sphere, okay? Flat Earth theory was proved wrong a long time ago. And we know that the inner core is a solid iron core. Then we have an outer core, the lower mantle, which is solid or plastic, the upper mantle, which is also solid or plastic, so it's a bit more malleable than the lower mantle. That's where we have our convection layers occurring, okay? It's also known as the asthenosphere, okay? So they're solid but mobile, so it's normally referred to as plastic. And then right on the outside we have a tiny thin veneer of crust. And like I said last day, there's two main types of crust, continental crust and oceanic crust. Okay? Continental crust is usually made out of felsic or intermediate rocks. You do get some basalts, like for example the Deccan traps or the Siberian traps. They're continental basalts, and they either will form from rifting, where you have the continent ripping apart, so kind of like the East African Rift Valley, or there'll be a mantle plume underneath. So there are a number of different ways that you can have that happen. Usually we have things that are called hotspots. Okay, so for example, the Hawaiian island chain is made of basaltic hotspot. Okay, where there's just superheated remnants in the mantle, probably from a asteroid impact that's just left that particular area of the mantle superheated, and it forms like a little chain of islands as the plate moves over the top. Just a notification that apparently you can buy one, get one free Domino's pizzas. Anyway, so that's how that island chain formed. There's also a number of basalts along the east coast of Australia that get younger the further south they are, and that's because there's a hotspot that is currently just to the north of Tassie. So as the Australasian plate has moved northwards, that hotspot has stayed stationary, and it's got a few little basalt flows out on the surface in a number of different places along the east coast. So how did we start to develop the idea of continental drift or plate tectonics? So I'm sure you guys probably remember being in primary school and literally doing the cutting out of the different continental plates, and you can put them back together and see that they're really similar in shape. The jigsaw puzzle kind of thing. So in 1620, Sir Francis Bacon proposed that they were separated during the biblical flood. In 1858, a guy named Antonio Snider Pellegrini drew what was called the first supercontinent, so when those two were together. Alfred Wegener, he was the guy that actually started to look at the rocks. So instead of just looking at the shapes of the outsides of the continents, because we know that the shapes of continents change over time due to weathering and erosion and more deposition and things like that. So what he did was actually look at the different types of rocks in both Africa and East and South America, and he saw that they were very similar. And so that's how he proposed that those continents were once joined, and that was the first mention of the theory of continental drift. So if you have a look at, so slide 4 is just an indication of Snyder-Pellegrini's illustration of how the two continents were once joined, or multiple continents were once joined. Okay, so sorry, I shouldn't have touched that. No, I don't want pizza. Right, sorry. This is going to be a great video for you guys to watch. So slide 5 gives a bit of a background in Wegener and talking about how he came up with the idea and how he looked at the different fossils and the different rock types. Originally, the idea that was prominent at the time that because of the similarity of fossils and the similarity of plants and animals that exist, they thought that there was a land bridge in between the two continents. So Wegener's theory of continental drift was hugely outrageous and massive scandal. So he was the first person to show that the continents, well, he wasn't the first person, but he gave the name of the supercontinent Pangaea, okay, and said that they were all once together in that supercontinent, but he didn't have a mechanism for how they had drifted apart. So because he lacked the mechanism, he was totally, like, railroaded. And there's over 30 years of huge arguments about it. And even, so he used continental drift for the first time in 1915, and like there's publications from geoscientists in 1944 saying that it's a fairy tale and should be ignored, and it's bad for the students to think about things like that. So slide 6, and again, this is just like what I was talking about earlier. I love how science is constantly changing. Like, the thought of plate tectonics 100 years ago was ridiculous. They thought it was a fairy tale. Even less than 100 years ago. 1940s, that's not that long ago at all. So it's kind of crazy to think that in the last 60 years, plate tectonics has become a thing. Like, a proven theory. And we now have evidence to back up how it works and what it was, and so cool. I love science. I'm such a nerd. Okay, so slide 7 shows you what Pangaea would have looked like. Okay, so Wegener's Pangaea, the northern part of Pangaea is Laurasia, the southern part is Gondwana. Gondwana is important to us because Australia is part of Gondwana. Now, these pictures on slide 8 show roughly the shapes of the continents that they are today. Now, Australia wouldn't have looked like that during Gondwana. It would have been slowly developing, and you can see probably the eastern edge of Australia, while it was part of Gondwana, was just south of the green fossil, whatever that is, some type of plant. But yeah, so this is how they mapped Gondwana together. So they looked at the different plants and fossils and saw how they were, how they appeared in all of the different continents, and then just kind of stuck them together with a best fit type scenario. So during Gondwana, we were located much further south. okay, when we were part of Gondwana, so 500 to 180 million years ago. We were right next to Antarctica and the South Pole, okay, and we've continued to drift north ever since then. So the type of sediments that you see during those periods are really cold, frigid sediments. So, for example, when we go on our second field trip, the site that we're going to be looking at, we can see sediments that would have been deposited while we were part of Gondwana. And we know that because of the types of fossils that we're going to see. We see cold climate fossils, we see drop stones, we see heaps of evidence of frigid temperatures that we definitely are no longer experiencing. And so that helps us to infer then that Australia used to be significantly further south, which is really, really cool. So slide 9 is talking about a few of the different types of theories that were roaming around about how these fossils could have, and these plants and animals could have moved from one continent to the other. And all of them were initially considered a joke. So, like, the animals could have rafted across the sea on a random log, that there was a Isthmian link, so a land bridge, or just island stepping stones, and the islands aren't there anymore. And continental drift was considered a joke as well, because as you can see, the two dinosaurs whose hearts are broken because the plates have suddenly rifted apart. We now know that they don't move that quickly, but at the time it was seen as a joke. So if we have a look at slide 10, it shows you a bit of where the glacial ice and the glacial deposits are in those continents that prove that we were attached to Antarctica. And so there's lots of glacial deposits, and slide 11 shows them all in their Gondwana positions, okay, and where the extent of those, like, Antarctic glacial ice was. So the biggest problem with Wegener's continental drift theory was that he didn't have a mechanism of how the plates moved. He just knew that they had moved. So a guy named Arthur Holmes was the first guy to suggest subsurface convection currents. And so that was his suitable mechanism. So as the hot mantle rises, starts to cool down, it sinks again, and then it circles around like that. So that was his initial ideas for convection currents. But he didn't really have a way in how everything connected, and it wasn't a completely fleshed out idea. And so this was argued a lot, and because he didn't have the actual physical evidence to back up his theory, it just remained unproven until they started to do mapping of the seafloor. So once sonar was developed for originally tracking submarines during wartime in World War II, they developed oceanographic institutes, and essentially what they did is they were mapping irregularities, aka submarines, and the topography of the seafloor. So that mapping of the topography of the seafloor is what we call bathymetry, okay? And bathymetry is specifically that science of mapping the seafloor. And so they started to develop these oceanic maps showing the topography. And if these continents had broken apart, then there should be evidence in the seafloor. So where is this evidence? And what they found are what we call mid-ocean ridges. So mid-ocean ridges are submarine ridges that occur where the crust is tearing apart. So if you have hot mantle rising, the material above the hot mantle will be elevated, and as it cools, it will sink back down and travel away from the heated center. Okay, so what happens is these ridges they found run parallel to the areas where you would have assumed that the plates, if you cut them out and stuck them together jigsaw-wise, that is how they're parallel to that, which shows you the movement and how they've moved away from each other. So the discovery of mid-ocean ridges was a huge deal, and it started to lend credence to Wagner's theory. So you have these ridges that have a bit of a rift valley. They're heavily faulted because of how fast the material is moving, and also because of how once the material, the contact between the material that's still hot and elevated and the material that's cooled and is moving away, they form a bunch of faults and called Horst, which are called Horst and Graben faults, which we'll get to in later in the semester. But essentially that just means that there's two blocks, and one block's slid down on either side of the block that's in the middle. So the bit in the middle, which is our mid-ocean ridge, has the cooler basaltic oceanic rocks faulting and dropping down along the sides of that, and as they shift away. Slide 15 has some pretty cool diagrams showing you a cross-section of that, and then it also has a one of the computer-generated images of one of the mid-ocean, of the East Pacific Rise, mid-ocean ridge. And so they found these mid-ocean ridges, which started to, like I said, lend credence to Wagner's theory. So then, when people were still arguing, saying you don't know, how do you know that they're getting older the further away from the ridge? You're just spewing nonsense. So what they had to do is they started to look at the ages of the basalt and the oceanic floor as it shifted away from the mid-ocean ridges. So the first thing they started to do was look at the magnetism. So it's not consistent, but every few million years, the Earth's magnetism, so the poles switch. So what is now the North Pole will become the South Pole magnetically. And so what they did is they looked at the polarity of the basalt as it got further away from the mid-ocean ridge. And so there was a normal polarity, which is the polarity that we have now. We call it normal because it's what we have always experienced. And reverse, we don't necessarily know when it's going to swing back into reverse polarity, but we probably won't be here, so it doesn't really matter. I have high hopes for the human condition, obviously. So what they saw, the further they got away from the mid-ocean ridge, is that there were pairs of sequences of basalt extrusions that were normal, reverse, normal, reverse, normal, reverse. And so they could tell that from these different polarities that there'd been a sequential and consistent movement. And then what they started to do was date those basalts. So they started to take samples from dredging of the ocean floor and found that the layers of the basalt, particularly close to the ocean ridges, were really young, like really, really young. And then the further they got away, the older they got. So if you have a look on slide 17, it's showing you the average, like the approximate ages of the oceanic crust. The red is the youngest, so it's less than 20 million years. Heading into the blues and the purples, there's a little bit of purple to the north of the African plate. And like that's getting older, so into the 200 to 280 million years. Okay, so the first thing you'll notice is that as far as the Earth is concerned, 280 million years is not very old. When we have continental crust in Australia that's 3.8 billion years old, or 3.7 billion years. So why do we only have such young oceanic crust? What happens to it? It gets subducted, it gets destroyed. So there's a few more slides giving a bit of an example, a bit more detail into those features. So I'll just scooch on a little bit. Yeah, so they started to develop this idea of seafloor spreading and how it works, and that you have these feeder dikes that pour up hot molten mantle that spews out on the surface, and then you have new oceanic crust occurring, and because you have new material pouring out, the older material gets pushed away, okay, as part of our convection, okay? And so one of the other things that happens, because we have, the whole plate isn't going to move perfectly at the same time in the same orientation. You're going to have faults forming, you're going to have some parts of the mantle, some parts of the spreading ridge spreading faster than other parts. And so you have this whole big sequence of what are called strike-slip faults. So they're types of transform faults, which transform just means they go side by side, okay? Instead of a vertical fault, they're side by sides. The movement is side by side, I should say. And that's all because of the differences in spreading rates, okay? So slide 24 shows you an example of how that works. So if you go back to slide 17, you can see that the spreading ridges aren't nice smooth lines. They're really zigzaggy or jagged like steps. And the reason that they're jagged like steps is because of those faults. Okay, so you can see that parts of the spreading ridge have moved, well, the spreading ridge might have moved, but it also is spreading at different rates, which I think is really, really fascinating that we can tell that. And it's one thing that's always I've really enjoyed about seafloor spreading and plate tectonics and things like that. So we knew that new crust was being developed, but the Earth wasn't expanding, so it wasn't getting bigger. So that tells us that the older oceanic crust must be disappearing somehow, okay? So that's our divergent boundaries, how the plates start to spread and pull apart. That's a divergent boundary. There's a pretty nice diagram on slide 26 that shows those spreading centers, okay? Slide 28 is when we're starting to look at convergent boundaries, okay? So this is where instead of moving apart, we have two plates coming together. So when you have an oceanic plate meeting a continental plate, because the oceanic plates are denser, they're made of basalt, which mafic rocks mafic rocks are heavier than felsic rocks because of the iron content, so they're really dense, even if they're thinner. So the oceanic crusts tend to subduct underneath continental crust because they're lighter and more buoyant and thicker as well. So continental crusts they've had a lot longer to develop more material from like sedimentary processes and erosion and things like that. So they're thicker, they're more buoyant, and they just kind of sit on top while the denser oceanic crust subducts underneath. So when you have oceanic meeting continental, you develop what's called a continental volcanic arc. Okay, so slide 28A, picture A, shows how we start to have melting of our subducting oceanic plate. So typically you start to melt the sediments, so the oceanic sediments that have been deposited. So there's heaps of water in there, and also things like mud and silt and some sand, and that all starts to melt because it's suddenly being exposed to extremely high temperatures. And the presence of water decreases the melting point. So everything under there has a significantly lower melting point, so they melt much faster, and that melting leads up to starting to develop plumes, volcanic plumes, and that plume, once it's reached enough either heat or it's developed enough material, it will start to rise through the crust because it's hotter, so hot things rise, and it rises through the cool continental crust, and we'll start to have volcanoes developing above it. Image B shows an oceanic to oceanic crust convergence, okay, where instead of developing a continental volcanic chain, we develop a volcanic island arc. Now, the material that you have in a volcanic island arc, because you have mafic rocks and mafic rocks, you develop what's kind of like an intermediate material. So because you've got those marine sediments melting from the top of the subducting slab, you start to have those sediments intermingling and altering the chemistry of what you would expect would just be basaltic. So they're on the more mafic side of intermediate rocks, but they're still they're not felsic and they're not mafic. They're kind of in between. So we call them intermediate. When you have continental to continental collision, like you see in slide C, you essentially start to build mountains. So because continental plates are so thick and so buoyant, neither of them wants to subduct under the other. And so what happens is that you start to deform the material, and it gets folded, and there's faulting, and it's heavily deformed, and you start to develop mountain ranges. So the Himalayas are a perfect example of continental-continental collision, where the Indian plate has moved northwards and collided and started to, the material has nowhere to go except up, essentially. So there's ridiculous crustal thickening there. So Mount Everest is the highest mountain in the world, and I think it has, kind of like icebergs do, where like the beneath the surface is where the majority of the something or other, I don't know, dramatic line from Titanic. It's what's beneath the surface you need to worry about. I don't know. But it's almost 2 times as thick underneath the Earth's surface as it is high in elevation above sea level. So crazy thick continental crust there, which is just super cool. So what they started to discover is that because the Earth wasn't expanding and we were developing volcanoes parallel to the boundaries between these tectonic plates, that told us that because there's melting occurring, the material had to be subducting underneath and developing the melting that's causing these volcanoes. So after they started to do that, they had a look around at which way they thought the plates were moving and how they could tell that. Okay, so we can look at our spreading ridges, which tells us which way they are spreading. So they mapped out all of the spreading ridges, which told us the boundaries, so that essentially the mostly oceanic boundaries, but there are other boundaries that are continental that they had to look at as well. Okay, and so how did they do that? They started mapping things like the Hawaiian chain, or series of volcanics, or like, for example, the igneous material in the Himalayas. And they could tell the orientation of plate movement. And it's really fascinating to think and see how fast and the orientation some of these plates are moving. So once you figure out which way the plates are moving and how fast they're moving, it will help us determine any future continental collisions, or it helps thinking about earthquakes and volcanoes and things like that. So Indonesia, for example, sits on the top of the boundary between the Australasian tectonic plate and the Pacific plate. And so there's subduction and earthquakes and all sorts of things occurring there, and volcanoes and all sorts of fascinating, interesting things, because the plates, they're not necessarily moving towards each other, but the Pacific plate is moving to the northwest and we are moving to the northeast. So we're kind of colliding on a T intersection kind of thing, which is pretty fascinating. Japan, for example, is in, oh man, it is in like one of the worst places. It's like the combination of 3 or 4 tectonic plates, which is why when they have earthquakes over there, they have big scale earthquakes and they cause heaps of damage because of how, I guess, volatile that area is as far as plate tectonics is concerned. So we talked a little bit today about deformation and how that sort of occurs. So slide 34 gives a basic introduction to the different types of deformation that you can have as far as regional metamorphism is concerned. So you can have compressional stress, where you're essentially squishing a rock. You can have tensional stress, where you're stretching a rock. And you can have shear, where you're moving sides by sides. Okay? So depending on the type of strain or stress, you will have different types of things occurring. And also depending on the type of rocks that you have. So some rocks react more malleable, okay? So they're more likely to bend and fold and behave in a ductile or elastic manner than other rocks. So for example, things like granites. If you fold a granite, it's more likely to fracture and cause faults than it is to fold nicely, because it's made up of really hard material. Compared to something like a mudstone or a sandstone, they're much more likely to fold and behave ductilely because they're not crystalline like igneous rocks are. They haven't crystallized from a melt. They're not perfectly interlocked grains. They're just fragments of detrital material that are stuck together with a sediment. With a cement, sorry. So all rocks behave differently. So with spreading ridges, if you go to slide 37, this is essentially showing you what's happening in the East African Rift Valley at the moment. So we've got tensional stress pulling the crust apart, and we start to see all of these faults developing. So these dark lines that you see are faults that have formed, and the material has shifted on either side of it in relation to each other as the crust is getting pulled apart. And so that initial spreading that is occurring, that original tensional stress, is usually formed by an upwelling of hot material under the surface, okay? And it starts to push the material apart as we have this convection currents working. So we start to develop those rifts, so like the East African rift. Eventually that will spread far enough that they'll start to have a small sea in between two continental crusts, so it'll get deep enough that they'll start to have sea in there, ocean waters. And then eventually, as that continues to spread, we'll have a fully developed mid-ocean ridge developing. So it's all to do with how thin the material above that upwelling gets, and once the upwelling breaks the surface is when we start to develop our mid-ocean ridge. So yeah, slide 38 is a really good diagram of how that works. So the prac that we're doing today, and by today I mean on Thursday, it's been too long already, we're going to be looking specifically at hotspots. So we're going to be looking at plate tectonics and how we know how fast a plate is moving by looking at hotspots. So knowing that what we know about igneous rocks, we know that we can give them specific dates. So if we have an island chain that has developed, we can do specific dating for all of those, with radiometric dating with our igneous rocks. And we can determine how old each island is, and by using age over time, age over distance, sorry, we can calculate how fast that plate has moved since those two islands were developed. So it's really, really fun and really cool, and that's the kind of thing that we're going to be doing. So slide 39 will probably be handy to think about when we are doing our prac on Thursday. So because with our spreading ridges, the plates can't continue to move forever without interacting with something, so they're going to collide with something in some option or another. They're going to collide either oceanic to oceanic, oceanic to continental, or continental to continental, depending on what's on the edge of your continental crust, of your plate, sorry. So when we start looking at the other side of things, so let's have a quick look at some of the convergent boundaries, okay? So the Himalayas, great example of continental to continental collision. The Pacific coast of South America is an awesome example of oceanic continental, and the Japanese islands are a great example of oceanic convergence. So on slide 42, we'll see that looking at the differences between where our collision zones occur and our extensional zones occur. You can see, if you look directly at on the right-hand side, the earthquakes and the volcanoes occur very similar positions. So if we're looking at the Pacific Ring of Fire with our volcanoes, which is that whole big ring of ridiculous numbers of volcanoes that occur around the Pacific, the majority of those volcanoes occur from subduction. Okay, so we have subduction occurring as the Pacific plate moves to the northwest. Okay, so we have the Australasian plate moving northwards underneath that plate, which is causing the island chains of New Zealand, Indonesia, and a stack of the other islands further along. and then we have places like Japan developing as the Pacific plate is subducted underneath other oceanic plates. I can't remember all of the names of the plates, there's way too many, apologies. But anyway, we have this occurring. A lot of earthquakes occur exactly over the top of these collisional zones, which makes sense because when subduction is occurring, it doesn't occur without stress. So you're pushing two really big, heavy hunks of rock against each other, and they're fighting for dominance, I guess. It's kind of like a really, really, really slow car crash. If you were sitting in your car facing another car and you slowly accelerated towards each other, you would still deform and crumple your cars. Okay? And so that's essentially what's happening here. A really slow deformation and crumpling of the Earth's crust. And you can see the heat flow signature doesn't correlate with where the volcanoes are. The heat flow signature shows along our spreading ridges. So the hottest areas that we have are those spreading ridges, which makes sense because it's essentially the mantle spewing out on the Earth's surface, which I think is really, really cool. All right, so our deformation. So we're starting to have compressional stress here. So we're having collision occurring. We're having compressional stress when our rocks are crumpling up against each other like the bonnets of two cars. Okay, so we start to have folding occur. Okay, and when you reach, so all metamorphic and sedimentary rocks will behave plastically to a certain extent. And I say plastically as in, think about like solid plastic rulers. They will bend a little bit, but they will snap if you put too much force on them. And that snapping is how we get faults developing. Okay, so faults that are caused by compression occur because we're pushing too much pressure on our plastic rocks. Okay, and so we start to get these faults and a lot of folding occurring, like in the maps we were looking at today. And when we have, so for continental collision, best example being India colliding with Eurasia, there are actually oceanic sediments on top of the Himalayas, which is really cool. Some of the highest points on Earth have oceanic sediments. And that's because of what was called the Bathurst Sea. Got essentially, it was some of the original material to get smushed up first. So there's, we'll talk about this later. We actually specifically go into talking about the Himalayas. But yeah, so it's really cool. We've got continental collision occurring. The Peru-Chile Trench is an excellent example of oceanic continental collision, where we've got that beautiful continental volcanic arc developing on the western side of South America. Okay, oceanic crust collision, looking at the Japanese archipelago. So slide 46 is just having a quick look at that, and we'll talk a bit more about the Japanese archipelago later on in the semester as well. We have a look at some of the reasons that we had big issues in Japan. Yeah, so when we have our continental or oceanic continental or oceanic subduction zone, I mentioned that we have intermediate lavas. And these lavas, because like I said, they had a lot of water in the sediments that were melting, they have a lot of gases within the molten rock. okay? And so those eruptions tend to be explosive. So they also form the typical mountains that you're used to, the typical pointed, peaky mountains, because their material comes up, it explodes, then comes back down. And so it develops this layered sequence with the highest point having the most material being deposited back on it quickly. Which is totally different to, say, the volcanoes in Hawaii, which are really low and flat-lying and really, really wide, and they are made of, like we'd said, basalt, they're mafic rocks, and that just flows, like the lava flow of a basalt flows completely different to the lava of an intermediate or felsic composition. So, if I was to compare the two, it would be like comparing how, like, I guess honey and water would probably be a good example. So depending on how much silica content there is in lava, well, like in the igneous material, depends on how sticky the flow is. And so silica forms these tetrahedral chains where they just form these like flat planar, not necessarily flat, but they form sheets, okay? So the silica and the oxygens share electrons, and so they stick together in weird ways. And so the more silica you have in a rock, the stickier it is, and the harder for it to flow. So something like a felsic rock or an intermediate rock is going to be a lot stickier because it has a lot more silica in it, compared to something like a basalt, which has very little silica in it at all. So basalt lavas flow real fast, real quick, like if you were pouring water out on a surface, okay? Which is why they are really low flat-lying shield volcanoes. And felsic rocks and intermediate volcanoes, they only flow short distances, which adds to this pointed shape or conical shape that you're used to seeing when you think about volcanoes. That's probably a lot of extra information, but it might come in handy a bit later on when we cover some more of this stuff, specifically week to week, okay? Right, that's fine. Slide 49 is pretty good. It might be one of those things that, I don't know if you like to print things out and stick them on the back of your bathroom door or on your wall or something like that, but it's a really great summary of how plate tectonic works and the type of rocks that you see developing due to plate tectonics. So I recommend having a good look at that and seeing how and where we see different types of rocks appearing. So I've mentioned the East African Rift Valley. So slide 51 is talking about that. So that's where we're starting to see spreading, and eventually the Red Sea and the Gulf of Aden are going to start flowing into the newly developing rift, and we're going to see ocean deposits in there soon enough. The San Andreas Fault is an example of a transform fault. Okay, so slide 52 is giving you a brief introduction into transform plate boundaries and how that is how they work. Oh boy. So essentially, that's from shear stress where the plates are moving past each other and fracturing and faulting because of it. Slide 54 is also another good example of what you might want to have a printout of that one and have a look at it. It's pretty good, shows you where you have all your trenches, where you have all your different types of plate boundaries, and also the direction of plate movement. So what then is the driving force of plate tectonics? We've talked about a number of different things. So mantle convection, where we have uplift occurring. Another thing that occurs is when you have the oceanic crust subducting underneath the continental crust, because it's been subducting for so long, there tends to be an excessive weight within the mantle. So there's a little bit of what's called slab pull, where the oceanic slab pulls a little bit the closer it gets to the sunken material. So you get a little bit of elongation occurring the closer you get to your trench, your subducting trench. And so slide 56 shows a bit about that. So we've got a bit of slab pull occurring. We have convection occurring that's forcing the ridge apart and the material to move. Another thing that happens is that as far as plate tectonics is concerned, the only thing that doesn't move are hotspots. So everything moves around hotspots. So you can have a mid-ocean ridge spreading but migrating at the same time. So it can be spreading at 6 centimeters a year in both directions, but migrating 2 centimeters a year to the east, which would make the apparent plate movement, it would look like the plate is moving 8 centimeters to the east every year, and the plate on the western side is moving at 4 centimeters a year, just because that spreading ridge is migrating as it spreads. It's a bit of a complex concept, but I'll go through it again on Thursday, so don't stress too much about that. But yeah, so there's a number of different things that these plates do that cause different types of movement. Slide 57 shows you diagraphically how fast each plate is moving in centimeters per year, depending on the length of the arrow. As you'll see, the majority of plates move less than 5 centimeters a year. There are exclusions to that, of course. The Pacific plate, I think, moves about 9 or 10 centimeters a year. And the Australian Indian plate is also moving probably a bit less than that, probably about 6 or 7 centimeters a year to the northeast, I think. Yeah, so the last slide is just a bit of a what will happen in the future, what are these plates going to be doing kind of thing. So it's just kind of cool to be able to look at mathematically and figure out from what we know of the past and how we know things are working now, we can predict the future. And I don't mean this in like tomorrow's lottery numbers. I mean like we can predict where these plates will end up 250 million years from now. The only thing that could throw that out of whack, giant meteor, or like planetismal collision, which would totally mess up with all of our plate tectonics and cause lots of fun for everybody. And by fun, I mean instant death. So yeah, so that concludes that lecture. Hopefully I've given you enough information to go on here. I know that this video is a lot longer than you probably hoped to watch. But hopefully you've made it through, and I'll see you guys on Thursday.